So how can I discuss the dimension of a vector space? And also, how can I find a basis for a vector space? Where should I begin? So here's the idea. I'm going to skip a couple of these little activities. The idea is that if you give me a set of vectors, and if I discover that that set of vectors is not a basis for the space in which it resides, then chances are either it's not going to be a spanning set, or it's not going to be linearly independent. If it's not a spanning set, it means we don't have enough vectors in my space, right? I need to throw some new vectors into that set in order to span what I'm trying to span. But a lot of times, it is a spanning set. It's just too big of a spanning set, right? I have too many vectors. So it has enough vectors to describe the whole space, but it has too many to be a linearly independent set. And so usually the strategy is to take a set like that, which is a spanning set but not linearly independent, and go in and find vectors that we can take away so that what remains still spans the whole space, but now is linearly independent. So find the members of that list which not only explain the entire vector space, but they explain the other elements in that list that depend upon them. So in this example, say, we've got these three vectors, 1, 0, minus 3, 2, minus 2, 1, 3, minus 2, minus 2. And those vectors, when you find the reduced row echelon form of the matrix that has them as the columns, has only two pivots. And so it's not a linearly independent set, and also it doesn't span the entirety of three-dimensional space. But if I were to take that column that doesn't have a pivot and just throw it away, it's not going to change what happens to the first two columns in the process of finding the reduced row echelon form. And so if I throw away the original third column, it's also going to throw away exactly the third column of my reduced row echelon form. But if I do that, then every column that remains has a pivot, and I have a linearly independent set. So this is the recipe for how to find a basis if I already have a spanning set, but I don't have it being linearly independent. This is how you fix linear independence, is you just take away all of the original columns that correspond to the non-pivot columns of the reduced row echelon form. And after I take away those original columns, what remains is a linearly independent set. So here's the next activity for today. Here is a bucket of 4 vectors in 4-dimensional space. Your job is to figure out what is a basis for the span. Whatever subspace is being spanned by these 4 vectors, you can find a basis for it with that process. Let's make this a 10-minute activity, or if you finish sooner, we'll come back sooner. So you found that when you took these 2 sets of vectors, and we did a different activity than I planned on because I didn't realize that I had solved 272 already as part of the thing. So we did 275 instead with these 2 different sets of vectors. And one thing that's interesting about them is that they're not actually that different from one another. Did you catch that these 2 sets of vectors have a lot in common with one another? What's the relationship? This is the same set of vectors, just ordered differently. And the thing about sets in mathematics is that sets don't care what order you list their elements in, right? An element either belongs or it doesn't belong. It doesn't really have an order. Sequences have an order to them, but sets don't. And so if I find the choice of which vector that I remove would seem to be a choice that might depend on how I order the columns of the matrix that I use to determine a basis. And so this activity is about that question. Should it matter if I order my vectors a different way? Am I going to get a different answer for a basis? And so when you do these calculations, when you do it the first way with the vectors ordered in the way that they're ordered in the set S up here, you find that the third column is missing a pivot. And so you end up throwing away the third column, and the third column is 1, 5, negative 1, 0. Right? So that one gets, that vector gets thrown away from the set. Oh, wait a minute. Sorry, I'm looking at the wrong one. The third column is 2, minus 3, 2, minus 3. And so that vector gets tossed away. And so your 3 pivots, your 3 vectors that are a part of your basis are just the first, the third, and the fourth columns of the original matrix. In other words, the first, the second, and the fourth vectors in my original set. So we threw away 2, minus 3, 2, minus 3. Then we tried it again, but we jumbled the vectors around so that they were in a different order listed in the columns. And when I do that, I find that the fourth column is the one that ends up missing a pivot. And so we end up throwing away this time, not throwing away 2, minus 3, 2, minus 3, but instead throwing away 2, 3, 0, 1. And so we're getting different bases for the space by just ordering the vectors in my set differently. Should this cause us trouble? Like, does this feel like it's a bad thing? One of the things mathematicians always try to do is make sure that whatever choices that they make in the process of solving something, that if those choices are supposed to not have an impact on the outcome, then they should not have an impact on the outcome. But somehow, it seems like just putting my vectors inside of the columns of a matrix in a different order, even though that shouldn't matter because we're just talking about a set, it's giving us a different basis. So what do you make of this? Lesson number 1 is that there can be, in fact, there always are, in any positive dimension vector space, more than one basis that we can choose. And so there's not just a single basis that's possible for a given vector space. So that's lesson number 1. Lesson number 2 is that we can get different bases that describe the same space, right? I mean, that's just a sort of a rephrasing of lesson number 1. And so the fact that in one case we threw away the vector 2 minus 3, 2 minus 3, and in the other case we threw away the vector 2, 3, 0, 1, we're still getting two different bases for the same vector space. So the vector space that's getting spanned is the same vector space in both cases. And so the last lesson relates to linear dependence, right? That if we go back to, let's say, this example where we have a plane inside of three-dimensional space, and I have three vectors that are coplanar, so they all reside in the same plane. I can write one of them as a linear combination of the other two. Right? So I could write this vector here as a linear combination of the other two vectors that are inside of this plane. But it's also true that I could write this vector as a linear combination of those other two. And I can write this vector as a linear combination of the other two. Right? So which vector it is that's redundant of all the others is not well defined by the definition of linear dependence. A linear dependence is a non-trivial linear combination of all three of these vectors that adds up to the 0 vector. Right? And so that doesn't single out any one of those three vectors as being the one that's redundant. It's just telling me that one of these is redundant with the others. And so whichever one of them I choose to remove, I'm not changing the span of the vectors that we have in our set. So I guess the good news is that we don't need to sweat that choice. We don't need to make sure, oh, let's get the vectors in the same order, or else we're going to get something that's not a basis of the thing that we want. It will still be a basis of the thing that you want. And so we can actually turn this to our advantage a little bit. Right? If I have a vector that I feel like I probably want to be the one that gets removed, maybe I'll try and put it in a position in the matrix that makes it the one that gets eliminated, the one that ends up without a pivot. That doesn't always work because maybe it actually is legitimately independent of all the others that are in there. But sometimes it does, and then we can get rid of the one that we don't like instead of having to get rid of one that's sort of random and arbitrary.